Now we are in chapter 14. Uh, it is about the function of two or more independent variables. So far we are working with a function with one variable. For example, we have considered uh, demand function, a supply function, which is the relationship between quantity demanded and the unit price, or for the supply function is the quantity supplied it and the uh, unit price, right? So just like Q, which is could be the quantity demanded or quantity supplied, just a function of one variable P. Okay, so its value just depend on P. So now we're trying to think of a, like, take into account more factors that could lead to function with more than one variables. In other words, we will see that something must be related to more factors. For example, the production level of a factory may depend on both the labor force as well as the capital of the factory, right? So you have to think of more than one factor that affect a single quantity. And so of course usually when we think of a function of two variables, we may denote the function by z. Okay, z equal to a function of x and y. In this case, both x and y is two independent variables. Okay, and z is kind of dependent variable because its level or value depend on the x and y. And so since we are working with totally three variables, you have to work with the three-dimensional space. Okay, because last time when you are working with only y just a function of x, we are having only two-dimensional plane, one dimension for x and the other for y. But now we have additional dimension, so you have to uh, create one more room for the new dimension, so that you have to deal with three-dimensional space. So in this case, the graph of the two variable function z is kind of no longer a curve but kind of surface. Okay, the graph of the function z in terms of x and y is actually a surface. So as you can see from this representative graph for the function z, you see that okay, a pair of x and y just give rise to a point in the space. Okay, just like when x take value x0 and y take value x0, it will give rise to z0. Okay, so that corresponds to a point P in the space. Okay, so in the figure you can see, okay, when x equal to x0 and y equal to y0, that corresponds to a point in the point R in the xy plane, and then correspond to that point is the level of the function, right? So maybe it will take the level z0, so that you will create a point P in space. So when you choose a different, you know, when you choose a different pair of x and y, I think you're gonna, okay, let's say x1 is somewhere here, and then y1 is somewhere here. Okay, so that you're gonna have another point in the xy plane, and that will correspond to another point in the space, and that will exactly the z1, right? The label correspond to the pair x1 and y1. So when you think of all possible value of x and all possible value of y, that we trace out into a surface, not a curve anymore. So in general, the graph of a function with two variables is kind of a surface in space. So let me trying to illustrate this using the uh, software, right, that I have prepared in advance. Okay, so for example, you may come up with a function of x and y, let's say z equal to x plus y. So what is the shape of the function? Okay, so if you look at this, this is actually it is in 3D, right? And this surface is actually the graph belong to this particular function, uh, z equal to x plus y. Okay, so it's kind of, if you just look at this, it's kind of a plane, right? A plane. Okay, a plane. So if you consider another function with two variables x and y, let's say z equal to x squared plus y squared, and this is actually the graph of that function. Okay, so look, z equal to x squared plus y squared. So when you choose all possible value of x and y, that will give rise to the surface like this for the level of z, right? So it just look like a, I don't know, but what can you say? It's kind of like a cup, right? It's kind of 3D figure, right? Surface, a surface, not a solid, but kind of surface. So if you just carefully observe this particular function, for example, if you forget about y, you just have only uh, z equal to x squared. So it should be kind of parable, right? Parabola, right? So if you just take a look at this shape in particular direction, for example, if you look at something like this, you will see exactly the parabola, right? If you just focus on the one direction, okay? In x direction, it's kind of a parabola, right? Or in y direction, if you just ignore x, you just focus on z equal to y squared, again it will be kind of a parabola in y direction. So totally it's kind of a surface that look like something like this. Okay, and how about this one? Y square equal to sorry, z equal to x square minus y square. So if you plot this curve, not curve anymore, I'm sorry. If you plot the graph of this function, it will be something like this. Okay, so look, it's kind of something like this. Okay, so this is kind of quick illustration of the plot of, I mean, the graph of a two-dimensional function. It's kind of a surface. It's no longer a a curve, right? So if you look back at the lecture slide, sometimes we just interested in one particular direction. Okay, so for example, this should be like, okay, the surface of a function z of x and y, but maybe if you just focus on a particular direction, for example in x direction, you may take y equal to a constant. Okay, y equal to a constant, and then you just let x vary. Okay, so just like you are walking on the surface in x direction, and you start at this particular point, right? Because if you notice, this point, all this point, okay, so can you tell me about the coordinate of this point? So they all have you know y equal to y0. Do you think so? And z equal to 0 because it is in the xy plane. The level of z is actually 0, and the level of y is actually always y0, right? And let's say this is x1 and this is x0, this is x2, for example. So all of these points just have the same y equal to y0. Just like you let y equal to a fixed value, and then you just vary x. Okay, so x kind of vary. Okay, it's changed, right? So just like you let y equal to a fixed value and then x vary, what happened to the surface? So it's just like a section of the surface. In other words, it's just like a curve, right? A curve. So this is actually the surface, but we just focus on a section. In this case, it's just like a curve, right? And likewise, if you let x to be a constant at x0, for example, and then you let y vary, then the you just come up with a section on the curve, on I'm sorry, on the surface, and in this case it's just like a curve, right? A curve. So why we need to think of this situation? We are trying to define what it means by partial derivative. Okay, partial derivative. So partial derivative, you have z equal to a function of two variables, right? So you want to see the change of z with respect to, for example, x, but when y is kind of a constant. Okay, you want to see the effect change of z once x change while y is keep constant, right? So just like if you think of in terms of graph, once you set y into a constant, let's say at y0, and then you let x vary, so what happened to the z? So just like you have to think of only this curve, right? So then the idea is trying to find what it means by the derivative of z with respect to x. Okay, you want to see how much z gonna change when you know the change in x, right? So as you know, derivative is nothing but a measure of change, right? So last time you have y a function of x, right? And then you have uh, dy dx, or it's kind of derivative. Okay, so this is measure the what? Measure the slope. Okay, measure the slope of the curve, and the slope actually the change, right? So what happened when exchange with this factor? What happened to the function? And now our function is z, and we want to know when exchange while y is kind of fixed, what happened to z, right? So we're trying to find a similar concept related to derivative, right? So in this case, if you're trying to let y equal to a fixed value y0, and then you just trying to measure the change of the function with respect to x only, just like you're trying to measure the slope of this particular curve. Okay, so this is just a curve, but of course it is a curve in three-dimensional space. It's a curve in space. Okay, but whatever the curve is, it must have kind of like slope, right? Because, you know, let's say you have this curve, and the slope at this particular point is nothing but the tangent, the slope of this tangent, right? Slope. So we're trying to define something similar for this case. So we come up with the idea of what? Partial derivative. So you want to measure the slope in x direction. Okay, so if you take a look at this figure, we want to find the slope at the point P. Okay, we want to find the slope of this curve at the point P in x direction. X direction is actually the slope of the tangent line AB, right? In x direction, right? You walk along the surface, but from like you're starting at y0 and walk along the x axis. It's just like in x direction, right? So what should be the slope at the point P in x direction? Or in other words, what is the slope of the tangent line? Okay, the tangent line AB, right? That will be eventually defined as the partial derivative of x or y with respect to x. Okay, so we denote that by this notation, and please see the comparison to come up with dy over dx. You compute the different quotient delta y over delta x, and then you let the delta x to be small, right? You compute this different quotient delta y over delta x, and then you let the delta x, the change in x, to be small, and then the value of the ratio will approach to a definite value we call derivative, and we denote it by, let's say, dy or dx, and of course that is actually y prime or f prime, right? Yeah. So likewise, we want to measure the slope in x direction, or the slope of the tangent AB at the point P. So maybe you begin with some kind of a different quotient like this, but in this case it's no longer the delta y but delta z, because our function is z, right? Delta y z with respect to delta x, and then you let this to be pretty small, and then it will approach to something like called the slope, okay, of the AB at the point P, just like in the figure. Okay, and we call that this one, we denote that by this notation, right? But you may complain that, okay, why don't we denote it by dz over dx rather than this stupid notation? Okay, actually it's a Greek letter. It's called dabla, right? but it's still something related to d, right? So when we are working with the slope or derivative, d is kind of special because to come up with derivative, we're doing different, right? Different. So as you can see, delta mean different in delta mean different, right? So when it's come to a small difference, we just replace delta by d. But now we replace it by double rather than d, and we refer to this as partial derivative. Okay, derivative of z with respect to x. Okay, and again, it's just like a slope, right? The slope of the tangent, but which kind of tangent? In x direction, right? But where? Because you have a lot of curve in x direction, depend on where you start. Okay, you start at here, okay, at y0. If you begin with a different y, let's say y1, you come up with a different tangent or a different curve, and that will be a different slope, right? So here we focus on the point x0 y0, right? X0 y0, and then you just vary x and let y to be a constant at y0, and in this case you come up with the concept called the partial derivative of the function with respect to x. And likewise, if you just, for example, you want to measure the change of the function z with respect to y instead, okay, just keep a x fixed at a certain value, let's say at x0, okay, and then you just vary y's, okay, you just change y so that y, the function also change. In this case, you just walking in y direction instead of x direction, right? So just like you here, right? You start here and then walk along the y direction, and then how you gonna feel the stiffness? Okay, how you gonna feel the stiffness? It's a slope, right? So again, you want to compute the slope at the point P, but in this case in the y direction. Or in other words, you want to measure the slope of the tangent line CD. Okay, CD is kind of the slope of the tangent to the curve in y direction, or to the surface at the point P and in y direction, right? So that gives rise to, let's say, this one. Okay, double z over double y, and just similar concept. We just call this partial derivative of z with respect to y, right? So when partial derivative mean, because it's just partial change, because total change must be change both x and y, right? Because z just a function of both x and y, but now we just want to see partial change of the function with respect only one of the variable while keep the other a fixed value. Okay, so that's why we name it only partial. Okay, partial derivative. And this is the notation for partial derivative. We use the double, okay, double notation, not the, to differentiate between the usual derivative and the partial derivative. Okay. So yes, double, right? Yeah. By the way, once you have z, just a function equal to f of x and y. So just like the letter z or the letter f is kind of the same thing, right? They are represent the function, right? So maybe sometimes you may think of double z over double x, just the partial derivative of the function with respect to x, or maybe you just simply denote it by fx, okay, fx, or just zx. So the subscript x means partial derivative, okay, and likewise the partial derivative of z with respect to y is actually denoted by this one, or either f sub y or z sub y, right? So they are all the same, right? So here the word partial means they just measure the slope only in one direction at a given point, not in both direction, right? Okay, so now when it's come to more than one variable function, the concept of derivative has been switched to partial derivative. And you may be curious on how to calculate the partial derivative when the for a given function, okay? So it's just pretty simple, right? So for example, you have this is like one example of a function of two variables x and y, and as you can see, the value of z just depend on both x and y, right? And then the first question you may ask, how to compute the partial derivative of the function z. So just pretty simple. If you want to differentiate z with respect to x, you have to let y to be a constant, or you can treat it as a constant, okay? So in this case, if you want to differentiate z with respect to x, then use the usual result from the usual derivative, or use the usual rule from derivative, right? So what is the derivative of x squared? 2x, okay? And how about this? So let's say you ignore y, so it's just like 3x squared, x cubed, I'm sorry. So what is the derivative of this one? So when you differentiate this, what will it be? What will it be? Please.
9x squared.
Yeah, it's gonna be 9x squared. So how about if I say, okay, ax cubed. So I said a just a constant. So what will the derivative? It will be 3a
3ax
x
squared.
squared, right? So now y squared is kind of a constant, right? Because you are differentiate with respect to x. So any other variable besides x is treated as a constant. So in this case, I think 3x cubed y squared is actually 3y squared x cubed, and then 3y squared is kind of constant, okay? Constant. So in this case, you're gonna have 9x squared and y squared. So you can see y squared just remain the same, okay? And the last term, y cubed, okay? Y is a constant, y cubed is also a constant. So when you differentiate it, when you differentiate a constant, let's say y equal to 3. So when you compute y prime, it's gonna be 0, right? So likewise, when you differentiate this term, and you know it is a constant of x, it does not it treat as a constant when you are think of x, right? So this kind of like something like 3 like this. So when you differentiate, it will be vanish, okay? So that's why you cannot see it, because it kind of 0, right? Yeah. So very simple. So how about the other partial derivative? Because you're gonna have two partial derivative, right? One with respect to x, and the other with respect to y, because the function is a function of x and y, right? So likewise, when you ask to differentiate z with respect to y, you have to, okay, treat x as a constant instead. Okay, so this guy gonna be 0 when you differentiate with respect to y, right? So that's why you cannot see something related to x squared appearing here. And how about 3x cubed y squared? So when you compute 3y squared with respect to y, that's gonna be 6y, right? 6y. And here, x cubed just kind of a constant, right? Because when you differentiate with respect to y, any variable beside y will be treated as a constant. So in this case, it's just like, okay, 6x cubed y. You see this? I hope you see this, right? And how about y to the cube? Okay, y cube is kind of simple, right? 3y squared, because you are doing a differentiation with respect to y. Okay, so look, it's nothing new. When it's come to partial derivative, you just make use of the rule from the usual differentiation. But just keep in mind that when you're working with a certain variable, treat the other as a constant. Okay, so this is just apply, not just apply to only function with variable, but it also apply to a function with more than 2 variables. Okay, so for example, the function z must be a function of x and y and let's say t, right? So when you compute the derivative of z with respect to x, you have to treat the other two variables, y in this case and t, okay, as a constant, just working with x only. Okay, yeah. So this is pretty simple. So if you have a good knowledge from the differentiation of one variable function, this is just like nothing new. Okay, yeah. So then we also think of the second order partial derivative, because like the one variable function, let's say you have y equal to f of x, the first derivative is kind of defined as y prime, okay, or f prime, or dy over dx, right? And how about the second derivative? You denote it by y double prime or f double prime, or you can denote it by d squared y over dx squared, right? So how to use this one? Because as I said, we have to use the d notation most of the time rather than prime notation to denote derivative, right? So for example, you trying to think that, okay, to come up with the second derivative, you have to differentiate the first derivative, right? It's kind of the derivative of the derivative. It will be the second derivative. And the way to denote the denotation is that the first derivative is kind of you differentiate with respect to x the function y, right? So just like d over this kind of operator, okay? It applies some action on y. And what it will be? It will be derivative. So likewise, to get one more time differentiation, you have to apply this operator one more time, right? Okay. And then you can see you have two d's, right? So t times d is kind of d squared. and y just remain y. And for the denominator, it's kind of dx with dx is kind of dx squared, right? So, but this is kind of analogy, right? Comparison. It's not kind of multiplication, right? I'm trying to make analogy, right? So that's why it makes sense to denote such a notation as the second derivative. And this also applies to the partial derivative. So once you want to have the second order partial derivative, you have to differentiate one more time with respect to x, for example, to this one, because this is like the first partial derivative with respect to x, and differentiate again with respect to x, and finally this should be a reasonable notation for the second partial derivative with respect to x. Okay, and we also have the second derivative with respect to y, and it's just like denoted by this way. Okay, yeah. And what they are actually, right? Again, when you are trying to compute the, the second partial derivative of the function z with respect to x, okay, this means that you keep keep y just kind of a fixed number, right? Yeah. So you just focus only the change in x. So you differentiate twice with respect to x. So that's why it measures the change in slope, right? It measures the change in slope. So this is just work equivalent when we are discussing for the function of one variable, right? So just like if you see that the slope is kind of negative, the second derivative is kind of negative, what can you say? This gonna be decrease, okay, decreasing, because if you treat this as a function and this is its derivative, right, and if its derivative is kind of negative, the function is kind of decreasing, right? So this is the case when the second derivative is kind of a negative, and if you look at the point P, the slope is kind of larger than the slope at R. So just like if you go along the curve in x direction, the slope just kind of decreasing. Okay, you feel decreasing. And if the second derivative with respect to x is kind of positive, I think that will be this figure, right? Yeah, this situation. As you walk along x direction on the surface, you feel increase in stiffness, right? So this corresponds to the second derivative of z with respect to x squared positive, right? So again, the way we analyze the change in slope for partial derivative in special direction just equal the same as the function with one variable, right? And the way to evaluate the second derivative is just pretty simple. Again, you just apply the knowledge from the function with one variable, right? So suppose you know that the first derivative is kind of 2x plus 9x squared y squared. If you compute the second derivative with respect to x, you have to differentiate this guy one more time with respect to x. And as you can see, this term will be 2, right? And this term will be actually 18x, because you differentiate with respect to x, x squared will become x. And the coefficient will be 9 times 2, right? So it will be 18. And y squared just treat as a constant. It will be the coefficient of the term x squared. So once you get a term differentiated, you're gonna come up with this. Term, right? Yeah. And similarly, if you know that the first partial derivative with respect to y is something like this, then the second derivative with respect to y gonna be something like this. Okay, so here differentiate again with respect to y. So this is just like a linear term in y. So once you differentiate, you get only the coefficient, right? 6x cubed, and this gonna be 6y, right? And this is like the possible notation for the second derivative, right? So you have to, if you want to use the Laplace notation, that should be something like this, and this gonna be familiar, right? You're already familiar with, because you are working a lot with the denotation, right? Yeah. And this is like, if you want to simplify the notation, you just state something like this, means you differentiate with respect to x twice, okay, 2 times. Or maybe you use the z rather than f, but of course they are refer to the same function, right? Both z and f, right? Okay, and this is notation for the second derivative with respect to y. So any questions so far? Any questions? But by the way, calculation is one important thing, but interpretation also still the most important thing that we gonna need when it's come to application. Okay, but rather than think of try differentiation with respect to x or with respect to y, you're gonna have something more we call the gross partial derivative. Okay, what is the second order gross partial derivative, or just simply called the gross partial derivative? Okay, because you know, you have two, right, variables x and y. So maybe on the first time you differentiate with respect to x, and on the second time you differentiate with a different variable y. Okay, so that's why you see here. Okay, so this means that first you differentiate with respect to x, and at the second time you differentiate with respect to y. Okay, and in effect this will be denoted by something like this. We have Laplace square, means you have to do twice partial derivative, right, of the function z, and the order is can be read in this way, right? Disappear first. So this means maybe first from the right. I'm sorry, right? They appear first on the right, so this means that you differentiate with respect to x first, and then with respect to y, right? Yeah. On the other hand, you may have the switch order, right? The opposite order. First, you differentiate with respect to y, and then with respect to x. And in this case, we denote it by this way. And take note the difference between the notation of the two. Okay, it's just like the order of the Laplace x and Laplace y, right? So this tells us the order of differentiation. Okay, yeah. So I don't know, but maybe you can think of the interpretation of the cross derivative. what should it be? So let's say this is the case when you let y fix. Okay, this guy is kind of fixed. So just like if you're interested in partial derivative with respect to x, it's just like you walk along the surface in x direction. Okay, this is of course a surface, right? But when you just walk in this direction, you start at y0 and walk along the curve. It's just like simply you just walk on this particular curve. Okay, of course you are walking on the surface itself, but once you fix the direction, let y just fix, not change, and just vary on the x. I'm sorry, x on the x. It seems that you reduce from walking on the surface to only this particular curve. Okay, so this is gonna be the slope. The slope of this curve, let's say the slope at the point P is kind of the slope is tangent line, right? So the next time you differentiate with respect to y, it's just like you let y change while keeping x fixed instead, right? So just like you just focus on the curve, sorry, the slope for each curve, and you just go through this direction instead, right? It's just like you change direction. Then you are working on the change in slope in a particular direction, right? Okay. Sorry. If you differentiate with respect to x again, that's gonna be the second partial derivative of the function with respect to x. So that will be you are still walking along the same curve, but you measure the change in slope, right? In x direction. X direction. That will be the second partial derivative of the function with respect to it. But now it's kind of cross partial derivative. So first, you think of the slope in x direction, and then you switch to change in y. So that's gonna be you focus on the change in the slope in particular in this direction, right? So I don't know, it's a little bit harder to figure out the meaning, but maybe you can think of something like this. Okay, yeah. So yeah, I think we don't have to discuss this again, but luckily these two guys are the same, right? You don't have to care about the order. Okay, you don't have to care about the order of differentiation, whether you differentiate with respect to x first and then y, or y first and then x. They will be they will result in this exactly the same value, right? So we refer to this as Young theorem. Okay, very surprised, right? Very surprised. And uh, so maybe you can check the previous function to confirm that this is true. Okay, look, this is actually the first. I think maybe I need to. So this is actually the first derivative with respect to x, and then I want to differentiate the next time with respect to y. So that we denote it by dx and then dy, right? So in this order. So please help me to get the final answer. So differentiate this guy with respect to y, then it will be Please. It will be what? Anyone? This is actually the first derivative of z with respect to x. And the next time we want to differentiate with respect to y. So just look at this boxed expression. So what will it be when you differentiate this expression with respect to y? It will be, I don't see anyone. Are you with me? Just like I am alone here. No, not alone. 29 of you right there. So please, so just kind of derivative. So what is the value?
2x 9 squared to y.
It will be
2x plus 9x squared to y.
x squared to y. No. Differentiate with respect to y. To y. So 2x will be 0. You see so? Because x just in this case treat as a constant. So this gonna be 0, right? The first term gonna be 0. So maybe you don't have to write it down, but maybe for explanation I just write down 0. And how about the next term? It will be
18.
Yeah, 18.
Y.
X squared y. Okay, agree with this or not? Okay, and how about the other cross derivative? I mean, you differentiate with respect to y first and then y. To y first and then x. I'm sorry, y first and then x. So that will be excuse me. That will be from this one. Okay, so this is actually the first derivative with respect to y, and next time you're gonna differentiate. Okay, I'm sorry, this should be squared, right? The next time should be with respect to x, right? So take note the different order in x and y. So this is gonna be, okay, look at this, gonna be, okay, with respect to x in this case, gonna be 18 x squared y plus, okay, you differentiate this term 3y squared with respect to x, it will be 0, right? So look, they are identical, exactly the same, right? So no matter what order you are performing, you're gonna end up with exactly the same. So that's why we come up with this general result, okay? And we refer to it as kind of Young theorem, okay? Young theorem. So now I have introduced the concept of partial derivative of a function with more than one variable, and the way again just measure the slope, right? The slope, but in a particular direction, because if you are walking on a surface, the slope can be measured in any direction, right? If you just walking on a curve, in a plane curve, okay, let me mention plane curve, slope just kind of one direction, right? But it's just like surface. Surface can be, say, like the road or the mountain, right? So maybe if you step on a particular point on the mountain, the slope just depends on which direction you are walking, right? Which direction. And of course, there are infinitely many directions, but we just focus on two major directions. So let's say the south north direction. Maybe you can call it the y direction, or the uh, west east direction, or the x direction, right? Because when it's come to surface, there should be two major directions. But of course, you may think of, okay, why not this direction? Why not this direction? We have infinitely many directions. So just like the partial derivative, just like measure the two major direction uh, among the infinitely many of them. So uh, okay, so I think let's stop here for a while to break, because maybe you need some time to break, right? Since you've been working hard for your quiz. So any question before the short break for 20 minutes as usual? Question or what? It's still very silent right here in the class, as always. Okay, so 20 minutes break. Please come back again at 4:20. Okay? And we still also need to check attendance at the end of the session. Okay, enjoy your break. Okay, everyone, let's resume the class again. So please raise your hand to confirm your presence. Okay, so let me share the screen. Okay, yeah. So in the first session, we were dealing with a function with two variables, and also the concept of partial derivative, right? So partial derivative, you have to like mention which variable you want to differentiate to, right? So now let's try to model the two variable function as something in application for real life problem. So first, we may apply the function with two variables in economics as the production function. So what is production functions? So let's imagine we are working in a factory to observe some production of certain goods. Okay, so just like in a particular day, the factory tend to produce some kind of certain quantity of production, right? So just like what should be the factor that affect the or determine the production level or the quantitative of the good or the output. Okay, so of course there are a lot of factors that determine uh, the level of production in a single day. The first one that we may recognize is the labor force, right? The labor force. So labor force is the main input or the main factor for the production. So if there's no labor force in a production chain, we cannot produce anything. And there should be another factor like the material, the raw material, the machine, of course the money, right? The money, the fund, or even the location of the factory itself. But generally, it's hard to figure out the explicit relationship of those factors to the level of production. So we're trying to reduce those factors into a single factor as, let's say, the capital. Okay, so together with the labor force, we have another one important factor we call capital labor that combine everything related to, for example, the machinery. So in other words, for the production function, we assume that the production level just depend on two main inputs, the capital inputs and the labor input. And here, as you can see, we denote the production function as Q, okay, equal to F of K and L. So K here is called the capital, okay, capital input, okay, and L is kind of labor input. So usually you may think of capital input as machine hour, right? How many hour for the operation of the machine, because in a production, as you may think of, like we need machine to produce something, at the same time we need people to operate, right? So how much time we can operate the machine for this single day to produce something, and also how many hour of labor we have in a single day, right? So the capital may be usually in machine hours, and the labor input may be in worker hours. Okay, yeah, worker hours. So of course, as I said, should be more than two factor, but other factor besides labor we just reduce to only the capital. And what is it is? It measures as the machine hour, the operation of the machine. And Q is just like the output label, right? Output. Okay, the output. Of course, the output is kind of the quantity we produce. You have inputs as labor and capital. What should be the output? And in order it to be a reasonable production function, we have to assume some assumption known as neoclassical assumption. The assumption for it to be a reasonable production function. So first of all, we suppose that K, Q, K, and L can take any value. It could be any kind of something like this, right? It's just like can be any number, not only integer number. Integer number, I mean 1, 2, 3, or something like that. But here, Q, K, and L can be any value, even decimal number, right? Just like 3.25 or something like that. So this means by those quantities are infinitely divisible, okay, divisible. And the function itself is kind of smooth and continuous. Continuous means if you plot the graph, it's kind of a surface, no hole, right? Surface. And smooth mean, what it mean by smooth? So if you think of a curve, this is a smooth curve, right? This is not smooth, okay? Because there is a corner right here, okay? Corner, okay, corner, or pointy point, right? So to think of as smooth or being smooth or not, if you just throw a car or motorbike on the curve, you feel comfortable, right? Maybe it can go up or down, but it's kind of comfortable. But if you travel along a non-smooth curve, you feel uncomfortable, right? Because there's some pointy point, right? Yeah. And continuous means there's no disconnection, right? This is kind of this, okay, not continuous, right? Because you cannot draw the curve in a single go without lifting your hand, right? So it's not continuous. So continuous and smooth must be required, right? But when it's come to variable function with two variable, we are no longer consider of curve but a surface. So you may imagine what is meant by a continuous surface and smooth surface. So continuous surface means there's no hole, right? Yes. And smooth means just like you just go along a road, okay? Even it's not need to be flat, but it's kind of no pointy point somewhere along the surface. So this is assumption, but of course the smoothness means it's differentiable, okay? Differentiable. Differentiable means we can compute derivative, okay? So actually the smooth mean differentiable, okay, in terms of mathematics. And one more thing is that we need both inputs, okay, K and L, to produce output. This means that if one of them is zero, okay, one of them is zero, let's say the capital is zero, even you have the labor, you cannot produce anything, right? So if like one of them, one of the input is kind of zero, the Q is kind of zero, right? The level of the output is zero. So sum of both input needed to produce an output, right? This means that more or less we have to contribute both of the input to in order to uh, produce a certain level of output. If one of them is kind of zero, we cannot do anything, right? You cannot operate the machine without worker, right? Or worker cannot produce anything without any machine, right? Yeah. And another assumption is an increase in K or L with other constant always increase Q. So this means that if you fix one of them, I mean one of the inputs, if you fix one of them while increase the other, it will result in higher quantity or output, right? So for example, suppose a current situation we have a certain level of input, both labor and capital, and suppose that you have influx of more workers in your production, so that will make higher output, right? Yeah. Or on the other hand, if you just brought a new machine, right? Just like you kind of increase the K level, again, it will result in a higher quantity of output, even you keep the same number of workers, right? So this is something that is reasonable, right? Yes. In order to be a reasonable production function. And lastly, we refer to it as law of diminishing marginal productivity. Okay, law of diminishing marginal productivity operates. So what is in by marginal? So if you look at the word marginal, you get something familiar, right? Because we're dealing a lot with marginal when it's come to economics. So marginal is nothing but still derivative. But here we combine it with productivity. Okay, marginal productivity means the derivative of the production function. Okay, so what is our production function? Our production function is kind of Q equal to FKL. So there are two possible derivatives, right? First is the partial derivative of Q with respect to K, and the other is partial derivative of Q with respect to L, right? So both of them refer to as the marginal productivity. It's mean the derivative of production function, right? But later on we will specify which is which. For example, derivative, the partial derivative of Q with respect to K will be referred to as marginal productivity of capital, while the partial derivative of Q with respect to L is called marginal productivity of labor. Okay, so this is the key definition of marginal productivity. It's still kind of derivative, right? Yeah, and I will explain later what is meant by diminishing marginal productivity, right? Yeah. So, uh, so what is this slope of production function? Again, when it's come to application, you may use production function of as a function of two variable, right? Two variable of K and L, right? Capital and labor. And we define what is meant by isoquant. Okay, so what is isoquant? So for example, like you have Q equal to, let's say, F of K and L. And then what if you fix the output at 100? So you just simply take Q equal to 100. So there should be a number of level of the input K and L that resulted in exactly level of output 100. So this is mean once you get Q equal to a fixed number, this is like kind of implicit, okay, implicit uh, relationship, and you just say a function, right? Implicit relationship of K and L, okay? Because that should be the combination of the two inputs that will generate the output of 100. And I think that that should be a number of pairs of the two input, right, that will result in exactly the same output. And those relationship of the two input just refer to simply as implicit function of K and L. Maybe you're not familiar with the word implicit, but if you know exactly what it means by explicit, that is the opposite, right? Implicit is the opposite of explicit. So explicit means you can see it clearly. Implicit means something like ambit, right? You have to take a look carefully to see it clearly, right? So of course this shows the relationship between the K and L, but it's kind of not explicit. Okay, so for example, if you have let's say K and L, right? So if you have K equal to L square, it's supposed to be the, you know, the explicit relationship, right? Explicit function. And if you have like K square plus L square equal to 1, this is called implicit function of, okay, K and L. Okay, so look, what is the difference between the explicit and implicit? Implicit is just like you can exactly have K once you know L, right? For example, when L equal to 1, K is actually 1. When L is 2, K is kind of 4. Okay, you can get it quickly. But in the second relationship, once you know L, K is not shown explicitly, right? You have to do some more calculation, right? So just like here, uh, we refer to as implicit function of L in case. And what is called, of course, we call it isoquant. So the word maybe iso, you may call isoquant. Iso means equal, right? Quant means quantity. So isoquant is the relationship between L and K that resulted in the same quantity of output, right? So this is called the 100 isoquant. Okay, okay. This is called 100 isoquant, means the relationship between K and L that leads to output of 100, right? And and for example, let's say if you combine, let's say K equal to 50 and L equal to 40, that will lead to a Q of 100, let's say, right? So what if you increase K to 60? Please answer me. To maintain the same level of output, if you increase the K from 50 to 60, what should be L? it should be the same level, higher level, or lower level? It should be less than 40 or remain 40 or larger than 40, the label. Everyone? It should be?
Smaller than 40.
Yes, smaller, right? Because by the assumption of value, we have this one, the third assumption, right? Increase one of them while the other remain constant, will always increase the quantity. So to observe this assumption, if you know that if you choose K to be 50 and L to be 40, that will resulted in the output of 100. But if you want to increase K to 60, a higher level, and you want to maintain the output level, L should be something less than 40. So that should be like lead to this exactly the same output, right? So this is of course the what? The isoquant, the function of K and L. So what it should be? It should be a decreased function or increasing function. I mean, just focus on the relationship between K and L, or just simply say 100 isoquant. So it should be decreasing, okay? Because if one of them kind of goes up, the other tend to goes down. It cannot go up at the same time or just even remain the same, because it cannot, otherwise the level of output also increase too, right? So if you want to maintain the output, this means that if you want to recruit more labor into the production, you have to turn off some machine, right? Or in other words, if you buy more machine to operate in your production, you're gonna recruit less people, right? Or just like fire more worker. Okay, this is the meaning. So this means that isoquant is kind of a increasing function, right? Sorry, not increasing, decreasing. I'm sorry, decreasing. So this means the we call the rate of substitution. Okay, rate of substitution, marginal rate of substitution. So just like let's say if you increase the K from 50 to 60, and then the L will be decreased from 40 to, let's say, 35. So this means that 10 K equivalent to 5 L, right? Because 10 K will be replaced by 5 L, right? So this means like rate of substitution. Okay, rate of substitution. And M here mean marginal. I mean the derivative is kind of decreasing, right? So this is sure. And of course this is nothing but the derivative of K and L, right? Because you know that this is kind of the implicit function of K and L. So maybe it makes sense to compute the change of the K with respect to the change of the L, and that is nothing but the derivative of K with respect to L. And we refer to this as marginal because it is kind of derivative, right? Marginal rate of substitution. Okay, marginal rate of substitution is nothing but the derivative of K with respect to L. We want to know how much K gonna be replaced by a certain change of L, right? Just like here, K 10K will be replaced by 5. Okay, yeah. So this is kind of a measure of substitution. Okay, and okay, yes. So this is some like concept related to production functions. So next, this should be the reasonable shape of the production function. So look, it's kind of a surface, right? So this is the surface of the Q equal to F, K, and L. And one axis gonna be the labor, and the other gonna be the capital, and the labor is kind of the output labor, right? So it, it must be something like this. So this means that this is correspond to the case when K equal to 0, right? So this must be 0, right? Because the point here along a particular point on this line correspond to 0K, right? Yeah, 0K and L. So this means that if you choose K to be 0, the level of output must be 0 too, right? So that's why the surface just like stay right on the L axis, and likewise the surface also stay right on the K axis, because this means this particular point on this is kind of F of K0, right? Because this point just correspond to K and 0L, right? So if you choose L to be 0, the level must be also 0. So that's why the surface is right stick to the K axis, and when they are not 0, it will be a particular level, right? Yeah, you begin to have some output, right? So this shape is gonna be reasonable for the production functions. This is the isoquant. Okay, isoquant mean you want Q to be a fixed level, let's say fixed at 60, or fixed at 100. So if you choose Q, the output, to be a fixed value, so that means you have to consider what should be the pair of K and L that lead to the same level of output level, right? The same level of output, right? So that should be exactly the cut. Okay, the cut parallel to the LK plane. Okay, you have to cut the surface through the KL plane, so that you're gonna have something like this, a curve, right? A curve. So this should be a point correspond to a certain value of, let's say, 60, right? And this should be all the point correspond to, let's say, 80, right? Because they have the same level of output. So there should be a numbers of pairs of K and L that lead to the same output level, and they just form, you know, a curve which show the relationship between the K and L that lead to the same output. And this is of course the curve of the isoquant, right? So this is the Q 60. I mean the 60 isoquant, right? Isoquant. And this is another isoquant, let's say 100 isoquant, right? So look, it's just like a curve that show relationship between K and L, right? K and L. So we know that isoquant is kind of a decreasing function, right? Because if you want to maintain the output level, if you increase one of the input, the other input must be go down, right? So that's why if you plot the relationship of the isoquant in a KL, I mean the KL plane, the curve should be goes down, right? It must be goes down. Next, let's think of what is meant by short run production function. Usually during a certain of time for the factory, they may decide to increase the labor of the labor of the labor while keeping the machine remain the same. They may recruit more labor force, or maybe they have no choice, right? But only increase the labor force because to order more machine is not cannot be done quickly. So maybe a short period of time, the factory just experience of a constant number of machine while uh, uh, increasing the labor force or decreasing the labor force. So this means that a case kind of fixed, right? The machine just kind of fixed, and error gonna be vary, right? It's gonna be changed. So we want to measure the change of the production with respect to error, right? Due to the recruiting more people or fire more people, or while keeping the capital fixed, while keeping the same level of the machine, right? So that will be exactly the partial derivative of the product function with respect to L. Okay, with respect to L, and we just denote it by MPL. MPL here means marginal product of labor, the one I just mentioned a while ago, right? We have marginal productivity. There could be two of them. Okay, marginal product of labor, and the other one must be marginal product of uh, capital, and they are nothing but the partial derivative, right? Yeah. So marginal product of labor is actually the partial derivative of the product function with respect to the labor variable L, right? Yeah. So it is denoted by Deblac 2 over Deblac L, and you see it's defined in mathematics. The partial derivative now it has its own name, right? It has its own name. So what? It measures the rate change of the output with respect to the change in labor force, right? While the other remain the same, remain constant, right? While the capital remain the same. So sometimes we want to know, okay, what if I recruit one more people? What should be the increase in the production? What if I recruit more 10 more people, and what should be the increase rate, the increasing rate of the production? Okay, so that will be exactly the marginal product of labor, right? It's just like the derivative, right? Yeah. And this guy uh, tend to be diminishing. Anyone know the word diminishing? What does it mean? Diminishing. Diminishing mean decreasing. Okay, so let me explain why it's called diminishing. Why the marginal product of labor is kind of diminishing. So let's say uh, at a certain level, let the current level is kind of L0 is kind of 100, and then you wish to increase one more labor. Okay, let's say you increase one people, you recruit one more people, and it will result in okay, let's say this is L and this is Q, and it will be increase the output by 5. Okay, I don't know, but let's assume that, right? You hire one more people into your production process, then that will result in a more file output as a result. But the next time you recruit one more people, one more person, the output will be something less, just let's say only 4. If you keep rehire one more person or worker, then it will just result in lesser and lesser quantity, let's say 3, or maybe I can say only 2, right? So look, the kind of the rate, the increasing rate of the output with respect to the labor is not remain the same, right? So what happened? Why it's not exactly the same? Why it's not 5 again? Okay, it seems that one more person, one more worker will create additional 5 output, and the other should too, right? Another one should too. No, because in order to uh, uh, produce an output, we need not only the labor but also the machine. But look, the machine just remain fixed, so you just only increase the labor force. So just like the efficiency can tend to decrease, right? Tend to decrease. So this is meant by the marginal product of labor is kind of diminishing, and it is captured by the second derivative is negative, right? Just like if you want to measure the increment, which is of course the MPL, right? MPL, the marginal product of labor. If you want to differentiate with respect to L, you vary L again. You just add L, right? One more. So the increment tend to decrease, right? And decrease is captured by, so this means that this function is decreasing. Okay, it is decreasing. As you can see from this, we keep change increase by 1, but should just kind of decreasing. So a function is decreasing, mean its derivative is negative, right? So we capture this concept, diminishing marginal product of labor by the derivative. Its derivative with respect to L is kind of negative, right? Okay, so it makes sense. Okay, it makes sense. Okay, so maybe you can think of the other uh, situation, like you keep K fish, sorry, you keep L fish, but you're trying to increase the machine, but it's not like more, it's kind of less likely to happen, right? Because in practice, we tend to easy to recruit or fire worker than buying new machine because it's kind of more expensive, right? And you need times to uh, deliver the machine, right? But recruiting people is kind of fast situation, right? Okay, so again, that's gonna be called the marginal product of capital, while you want to keep L fixed and you want to vary K or the capital, and that nothing but the derivative of the uh, output function with respect to K. Okay, we refer it to as marginal product of capital, and again it must be diminishing, right? It must diminishing. We can explain with the same reasoning. Okay, the derivative is kind of negative, right? Okay, so look at again. Look at again this one. Since marginal price product is kind of derivative of Q with respect to L, and if you differentiate this one more time with respect to L, it will become the second derivative with respect to L, right? So this must be negative, okay? This must be negative. Okay, I think it is done for today, and next week we're gonna complete everything, okay? Because next week is the last you know the last week for the lecture. So please trying to capture the concept rather than